Hello and welcome to today's lesson on solving quadratic trigonometric equations. Before we dive into some trig equations, I'd like to just reconnect us back to some basic algebraic skills involved with factoring. In a situation like this where we have 2ab plus b equaling 0 and we're asked what values of a and b and or b make that true, that's what solving asks. What values of the variable make this equation true? Well, we know that since we have a b in both of those terms, we can common factor out that b. And if we do, we would divide it out front. Now remember, common factoring truly just means that we would divide it out of each term. We would bring it out front, and we would have left 2a plus 1 after common factoring. Now, the beauty of factoring is that it turns an addition of terms into a multiplication situation where we can look at each of the factors individually because we can use what's called the zero product property, that I only need one of these factors to be 0 in order to create a 0 out of both of them multiplied together. And so in this situation, we know that if the variable b is a 0, then it doesn't matter what a is, because then b will take care of creating a 0 on the left-hand side. And right back here, if b is in both terms and 0 is in both terms, then 0 plus 0 does make that original equation true. Now, for the other factor, we can look at it separately to say that, well, whatever it is that's needed here for a to create a 0 out of that factor, then it wouldn't matter what b is. Pick any b, and we'll solve with the value of a that creates a 0 here. And so what we do is we can pull out a single linear equation and solve that linear equation, subtract 1 from both sides, and then divide by our 2, and the value of -1/2 for a. You put a -1/2 in our original equation, -1/2 times that 2 creates a -1, and negative b plus b, whatever b is, you make it negative and then add it, it will create a 0 on that side. And so what we've done is, through the process of common factoring, it changes an addition of terms and remember, subtraction is just addition of a negative amount. Addition of terms into multiplication of factors, and allows us to make two linear equations. Now remember, we're doing this so that we can have a basis to move forward with trig equations in the same sort of logic. To make two linear equations. The same is true when we are dealt with a polynomial equation here, a quadratic equation. What value of x would I square it here and also put that same value here and do this math? What one or two couple values make that true? Well, the very first thing when we are presented with a trinomial, the very first thing in terms of solving this trinomial is to set it equal to 0. And when we use trig equations, it will be the very same pattern. So we'll subtract this 3x to the other side of the equation, subtract the 4 on both sides, set it equal to 0, and then we have learned that we can factor this situation. And again, trinomial factoring also turns an addition of terms, an addition of negative terms here, into a multiplication of factors. And so we've got x times x making our x squared, 4 times 1 making a 4, but if we want that 4 to be negative, with a -3 inside-outside collection of terms, so a -4x plus that 1x will create that -3x. Now again, I've created a multiplication of two factors that I can then look at separately, create a linear equation. What value in this equation makes it true? Well, it is an x of 4. if I add 4 to both sides, I know that putting in an x of 4, it doesn't matter that it makes a 5 here, because 0 times whatever this becomes will create a 0. And similarly here, an x plus 1, how do I make a 0 out of that? Well, we'll subtract that 1 from both sides, and we find out that another value that would make that original equation true, a -1 squared and a -1 here, creates an equal value both sides, or a +4 squared, creating a 16, and a 4 in here makes a 12 plus 4 is 16. Those values make it true. So this would also be trinomial factoring, doing this exact same thing. And so the very first step is to set it equal to 0. And then we get 2 linear equations. We get a linear equation here, 2 of them here, and 2 of them here that we can then go and solve. So let's dive into trig. Solving quadratic trig equations uses this same technique of factoring the equation and then finding the angle or angles which make the equation true. Now, let's take a look at this equation. The sine of a double angle plus the cosine of that very same x is equal to 0. And we want to know what x values, what angles would make that true from 0 to 2 pi. Now graphically, what this question is asking, if we take a look, for those of you who are so very visual, I have punched in my equation the sine of 2 times my angle x plus the cosine of x, and it comes up with this crazy graph. And so if we look at that crazy graph, what our equation has asked is, where is that graph equal to 0? Well, it looks like I have 1, 2, 3, 4 answers from 0 to 2 pi, and of course it is a repetitive pattern. It happens over and over and over again, as every trig pattern does. But from 0 to 2 pi, I am looking for 4 answers. 1, 2, 3, 4. Now, if we find them with Desmos, it looks like I'm looking for a pi by 2, a 7 pi by 6, a 3 pi by 2, and 11 pi by 6. So nice, exact radian values. So how am I going to be doing that algebraically? Because on a unit test, of course, we don't have the luxury of being able to dive into Desmos and get Desmos to find us the answers. And so what we want to do is get on a mission to create an equation that perhaps we can factor and solve the individual linear equations. And so right now, I don't have a single linear equation that deals with just one trig equation, nor do I have a polynomial equation where I have any squareds in it that I could trinomial factor. But what we do have is the ability to substitute in a known equivalent expression. We've been practicing our trig toolbox extensively, and I know that the sine of 2x, using our compound angle identities, we can create the equivalent expression of 2 sine x cos x. So let's put that in here. We've got 2 sine x cos x is the very same thing, an equivalent expression to sine of a double angle, and I have the cosine of x left over being equal to 0. And so I'm hoping that you see we have the opportunity to factor out a term that is in common. Our cosine of x is in both of those terms. And so let's divide it out, factor it out front. If I take it out of that first term, I'm left with 2 sine x plus, and if I divide it out of this term, I'm left with 1. Just like our algebraic situation here, dividing a b out of both of those, I'm dividing the cosine of an angle out of both of those because it's in 2 spots. Now I have changed an addition of terms in a trigonometric equation into a multiplication of factors. And just like up here, I could deal with them separately to find out what value of my variable makes the equation or that factor 0, which would make the equation true. Here I need to find the angle that would create a 0 value here, and the angle that if I took the sine of it multiplied by 2 and added 1, I could create a 0 here. And so if we pull this apart, cos of x being equal to 0, we could go to our unit circle, or if we remind ourselves very quickly of a sketch of the graph of cosine, we know that cosine starts at its maximum of 1, ends at its maximum of 1 in a 2 pi radian set of angles. What values are these where cosine is equal to 0? Well, right here and here, we know that that is our pi radians. I haven't drawn it fabulously symmetrical here, but I do know that these values would be halfway in between. And so we've got pi by 2 radians here and 3 pi by 2 radians here. And so because I have justified it with my graph, or perhaps you could justify it with a sketch of your squishing down triangle that we have used to evaluate what angle makes cosine 0, or your unit circle, give me something that justifies the fact that your angles are x being pi over 2 or 3 pi over 2. And so with that linear equation, we have found two of the angles that Desmos identified. We've found this pi over 2, and we've found the 3 pi over 2. So now we need to get the 7 and the 11 pi by 6's. And we will accomplish that with our next trig equation, our 2 sine x plus 1. How do I make that equal to 0? What angle would make that 0? And then it doesn't matter what happens over here, because a 0 would zero out both of those factors. And so I solve this as a linear trig equation. Let's subtract that 1 from both sides. Let's divide out that 2. And so I want to know what angle of x has a sine value of -1/2. Well, 1 and 2 are nice convenient values from our 1, 2, root 3 triangle with our pi by 3 and pi by 6 radian angles. Which of the angles here is my reference angle that would have an opposite over hypotenuse, an opposite 1? Well, we know that the opposite side length to pi by 6 is my 1, and so my reference angle is pi by 6, but I need to put it into a quadrant or quadrants where sine is negative. And so I can actually, sorry, I'm pausing because I see that I should have just done a little quick sketch to identify this with our graph, that if this is -1 and I'm looking for when is sine -1/2, remember making a quick sketch identifies about where our angles are, as well as the number of solutions that make this equation true. And so always drawing a quick sketch of our sine of x keeps us on the path to getting the right number of solutions, as well as being able to double check their relative value. We know that these are third or fourth quadrant angles that we're looking for. And so using cast rule, where is sine negative? Well, I know that cast rule reminds me that our sine value would be negative in this quadrant for where tangent is positive, and so we put our pi by 6 angle, our reference angle there, and there it is. There's one of our x values, and there are 6 pi by 6's in a half circle, and we're one past that, so 7 pi by 6's is the third quadrant angle that would allow for sine to be -1/2, and then again we put it into the quadrant where only cosine is positive, and so our reference angle always snuggles back to the x-axis, and so there is our mystery angle. There is the x value, and we know that a 2 pi radians, we would have 6 pi by 6's and another 6 pi by 6's for 12 in total, and so we are one short of 12, being 11 pi by 6's, and there we go. There's our answers. Therefore, x is going to be our pi by 2, our 3 pi by 2, our 7 pi by 6's, and our 11 pi by 6's. 4 angles make that original equation true. Okay, so let's take a peek at a situation that mimics what we had above, a quadratic trig equation. Very first step, I set it equal to 0. So we'll bring both of our terms over to the left-hand side. We'll have -3 sine theta minus 4 equaling 0, and we'll factor this expression just like we did the algebraic quadratic above. I know that sine of theta times the sine of theta gets me my sine squared theta, and I know that 4 times 1 gets me a 4, but I want a negative 4, and so a negative 4 sine and a positive sine comes together to be that middle term of negative 3 sine theta. And that allows me to identify two linear trig equations that I would be able to find my angles that create the values that would make the original equation true. And so the sine of theta minus 4 equaling 0, we'll solve that to get sine equals a number. And I look at that and I think, when is sine reaching a value of 4? When is sine 4? Well, that's never. There are no angles. My ratios only go up to 1 or down to negative 1. And so a value of 4 being up here doesn't have an angle that reaches that output. And so in this factor, there are no angles that make that true. There are no solutions. Sine of an angle never reaches 4. So let's go over here to identify our possible angle that would create a valid solution above. So sine theta being negative 1, oh, negative 1 happens right here. Negative 1, right there, we know that that is a value of 3 pi by 2. And so we do get our one answer here, 3 pi by 2. And we've justified it with a sketch. Again, you could justify it with your unit circle or your squishing down triangle, but there we go. And let me connect that graphically for you with Desmos as well. I took the time. Our equation was sine squared theta. When is that equal to a 3 sine theta plus 4? And so I inputted the graph of sine squared theta. There it is. And what our equation asks is, when is that graph equal to 3 times sine of an angle plus 4? So we'll turn that one on. And we can see that in our first cycle of 2 pi radians, let me just bring this down a little bit so you can see the repetitive nature of both of those graphs. Here's our graph of sine squared theta, and 3 sine theta plus 4 has this crazy graph here, where we get this repetitive pattern. And where are they equal to each other? In the first 2 pi radians, it's right here. There's only one intersection point where they are equal to each other at an input value of 3 pi over 2 radians. Then they would both of those equations would calculate out the positive 1. Okay, so let's look at a couple more examples. I've got the example here, another bit of a different algebraic strategy here. We've got a quadratic trig equation. We're dealing with one of our secondary trig equations, 3 secant theta minus 4, or sorry, 3 secant theta, when is that equal to 4 in the first 2 pi radians. And so what we want to do is, again, step 1, manipulate until you have linear trig equations from your factors. And so we take our equation, 3 secant squared theta equaling 4. Now some of you might try to dive right into cosine first. I'm going to leave that to the end. Let's get secant theta equaling a number. And so let's divide that 3 out of there. Secant squared theta equaling a 4/3. And we know that we could square root both sides in order to get rid of that square. But be very careful. When you square root both sides of an equation, you cannot ignore that there are two answers. There's a positive value and a negative value that comes out of the square root of 4 over 3. Now I'm just going to break this up into 2 square roots because we can get a nice answer out of the square root of 4. So we are looking for the positive and negative values of 2 over root 3, what being the secant ratio for theta. Now we know that secant is just upside down sine. Secant compares the hypotenuse to the adjacent. And so we have created 2 linear trig equations. let's deal with them separately. So I know that this would be, if I just flip this ratio upside down, my adjacent over my hypotenuse, I wouldn't be comparing secant anymore. I would be comparing cosine. And so we'll put our adjacent on the top and our hypotenuse on the bottom, and we'll consider the positive aspect that comes out of this scenario, as well as the fact that the cosine of theta, I've got to look at that negative value for the cos of theta. Step 2, we have to justify our situation, so let's make a good sketch of cosine going from its maximum. Actually, let me get 2 pi radians here. I'll try to make this symmetrical rather than just a quick and dirty sketch. So starts at its maximum, ends at its maximum. Pi radians would be in the middle at its minimum. Oh, that wasn't bad in the first place. This would be our pi by 2, and this would be our 3 pi by 2. And so we'll do a nice smooth curve through those favorite 5 dots of cosine. And so I am asking root 3 over 2. Now we know that the square root of 3 divided by 2 is our, is our 0.8660-ish. And I want to know the value of that being a positive value. So 0.8660, 0.9-ish. So positive root 3 over 2 and our negative root 3 over 2. So if we go over here, I'm looking for some angle on either side of pi that would satisfy the negative solution, and some angle fairly close to 0, as well as close to 2 pi over here. We have 4 answers. Now, I'm going to put these answers in orange, and these ones will illustrate in blue, just to keep it straight. And so step 3 would be to say, okay, I'm going to dive into cast rule. I need to have a reference angle. The adjacent root 3 and a hypotenuse of 2 comes from that same 1, 2 root 3 triangle. Our pi by 3 is across from the root 3. Pi by 6 is our smallest angle across from the smallest side. And so I look at that and I say, okay, well, what angle would have an adjacent square root of 3? And again, we've got our pi by 6 here that is adjacent to our square root of 3. And so then I dive into cast and I figure out, okay, I'm looking for both 2 situations here. So let's look at our orange situation where we've got the cosine of our theta value being equal to the positive root 3 over 2. And so I'm going to put my theta into the quadrants where cosine is positive. Cosine is positive in that first quadrant. And so I know that one of my orange solutions here is that same pi by 6 reference angle in that first quadrant, as well as the fact, don't need to rewrite that, I need to do another quadrant. Where is cosine also positive? Well, we do know that it's positive in that 4th quadrant, and so the theta angle that I'm looking for is a 4th quadrant angle, 1 pi by 6 short of a full circle. There would be 12 pi by 6s in a full circle, and so this one is 1 short, being 11 pi by 6s. And so there would be my pi by 6 and my 11 pi by 6 angle. And then, again, we are solving for those blue theta angles. Where is it? Negative root 3 over 2. And so root 3 over 2 reference angle for cosine is my pi by 6. And so I would plunk that into the other 2 quadrants where cosine is negative. So let's do the 2nd quadrant angle first. And the 3rd quadrant. So pi by 6 reference angle goes into both of those. And so there is my theta angle for my first angle here in my 2nd quadrant between pi by 2 and my pi radian set of angles. And another one here. This is 1 pi by 6 short of a half circle. Half would have 6 pi by 6s, so this is 5 pi by 6s, and this is 1 pi by 6 past my half circle of 6 pi by 6s, so we've got our 7 pi by 6s here. And so that is a 3rd type of strategy where we're not solving with common factoring, we're not solving with trinomial factoring, we are solving with our taking the square root of and creating two linear trig equations where we've got both the positive and the negative values. So below I have two equations that I would like for you to try. So if we could pause the video here, and I'd like for you to give them a whirl, and then we will reconnect back and go through the solutions to see if you've been successful. Now remember, there's not always one way to do the solutions for any math problem, so I'm going to present to you the solution that has worked for me and point out how we can get to what angle or angles make this equation true. Now, before I send you off to do that, remember, before you can trinomial factor anything here, you've got to get it into a single trig expression. So get it into all sine, or get it into all cos, or get it into all tangent. And then you can factor it either with common factoring, or factor it with trinomial factoring, or take the square root of both sides. So pause the video here, have some fun with this, and we'll reconnect back and go over a couple of solutions. Okay, I am assuming that you have had time to go through the solution set for each of these. So let's take a peek at a possible solution here. So I hope you took my advice that you want to create a trig expression that has all one type of trig expression. We know that sine squared x is the very same, or has the equivalent expression as 1 minus cosine squared. And we know that from our Pythagorean identity, where sine squared plus cos squared equals 1. And so we have created a situation where we're all cosine squared, so we'll get that into all onto one side of the equation and create this factorable situation, cos squared x minus 3 cos x plus 2. And if we factor that out, we can create two linear expressions where we can try to find the angles that make those true. And so the first one, where is the cosine of x, this is wrong, equal a 2? Well, we know that there are no solutions for that because cosine never goes above a 1 nor below a negative 1. However, the other linear trig equation, when is cosine x equal to 1, we do have two values for that. We have two values. Sorry, I got this wrong from last year. Just pausing here for a second. We have two values that make that true. We have the value of 0 and the value of 2 pi radians. And so we can pick it right off our graph. We don't have to do any cast rule analysis. Now I do want to also extend this into the idea that if this was not factorable, just like many polynomials weren't factorable, but they perhaps still had solutions, we could be asked to dive into a situation like, what if we had got this trig expression where there are no values of 1 or numbers that multiply to 1 that would get me a negative 3 as an inside-outside term. It would not be a factorable expression. That doesn't mean that there aren't solutions. What I would have to do is remember my friend, the quadratic equation, get my a value, my b value, and my c value, and run that through the quadratic formula that would allow us to be able to get the numbers that aren't quite so nice, and then I would have to use my calculator to find my reference angle that would allow us to go into a cast rule analysis. Okay, expression B. Let's take a look at perhaps how you might have tackled question number B. Cos of x minus secant of x, well, let's get it into all one trig expression. We can take secant of x to be 1 over cos, and then we are sitting in a situation where we need to make a common denominator. So we'll multiply top and bottom here by cosine to get cosine squared on top. We'll put that together as one fraction. And we can see that I have a chance. What did I do last year? I have a chance here to create a difference of squares as my factoring out the top of my expression. Now, if we multiply both of our sides of the equation by cosine, then we would have a 0 on this side. And I would know that my restriction down here, I cannot cough up the idea that cosine is, oh, that's where that must have come from last year, looking at where is cosine x. It's the value of pi by 2 and 3 pi by 2 would create a cosine ratio of 0. And remember, we can never divide by 0. So don't tell me in the end that pi by 2 or 3 pi by 2 are any of your answers, because a pi by 2 or a 3 pi by 2 would create a 0 here, and that would be an invalid solution. So if we look at simplifying our trig expression, multiplying both sides of our equation by cosine, then we get two linear equations, and I ask myself, where is the cosine of x equal a -1? Well, that would be right here at pi radians. And where would it be a +1? And again, we would get that 0 and 2 pi radians, and we can go from there. What did I also show here? Oh, we could multiply both sides by cosine here, and we could employ our strategy of taking the square root of both sides, but then don't ignore the fact that we've got a positive and a -1 coming out of the square root of 1, and again, we would still get our same 3 angles. Or, what have I done here? Multiplying by a -1. Oh, I must have got another solution from another student at times. I love the way your brains work to give me different ideas here. I have had a student in the past that looked at this and said, okay, well, what if this isn't 1 minus cosine? I could put sine in there. We totally could. If we multiplied both sides by cos and both sides by a -1, we would get 1 minus the cosine squared of x, which is sine squared x, and we would take the square root of sine squared and the square root of 0 and ask ourselves, where is sine equal to 0? And we would still get those same 3 angles of 0, pi, and 2 pi radians. And so there's multiple ways to get to the answer of that one. I'm hoping that now that you've seen it, you'll be able to employ some of those strategies as well. What I would now like you to do for the rest of the period, you can get yourself in pairs. And I've given you this little half sheet of solving quadratic trig equations. Feel free to tackle these later if you want some extra practice on these. I will present the solutions to these tomorrow in class. But what I want you to work on right now is the solutions to 7 to 11. These are sort of more indicative of the level 4 questions that you'll see on our unit tests. And I have put full solutions, and again, I've put a solution. It's not necessarily the only way, just like we have seen in that last question. There are multiple ways to present the solution. And I'd like for you to take a look at the solution of number 7 once you've given it a try, because I've given you a little heads up of what not to do, because we lose a solution if you take one certain strategy. And so I've shown you a couple of different strategies on how to be successful with question number 7. Once you are finished with 7 to 11 and you've had a chance to take a look at your solutions online, then what I would like for you to do is to dive into your homework. We've got lots of questions that you can be looking at and be solving those. And you can help each other out with those and bring any troubles that you have to tomorrow's class. Thanks so much, and we'll see you soon.